All right, subscribers, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is section 2.2, which deals with scientific notation and dimensional analysis. Now, before I get going into the details of these notes, I want to outline a couple of objectives that you should be able to meet by the end of this video. So objective number 1, express numbers in scientific notation. And objective number 2, use dimensional analysis to convert between units. So we start out here with this concept of scientific notation. And scientific notation is used to express any number as a number between 1 and 10. We call that the coefficient. And we multiply it by 10 raised to a power. We call that the exponent. Now, some general rules of thumb about scientific notation is this. When numbers are larger than 1, the power of 10 is positive. And when the numbers are smaller than 1, the power of 10 is negative. Now, let's see some scientific notation in a few examples. Our first example is the mass of the proton, which, if it's expressed in the units of kilograms, as it often is, there are 26 zeros before we get to a non-zero number. So the mass of the proton, if I write out that entire number, has 26 zeros listed before we get to a non-zero number. And it was so big, I couldn't even fit this on my piece of paper. Now, if we express this mass of the proton using kilograms, and we express it in scientific notation, the number becomes 1.62762 times 10 to the negative 27th kilograms. So again, this number now fits very nicely in a smaller space, and there's less of a chance to make an error by putting one too many zeros or not enough zeros in the correct spot. Now, another example is the mass of the electron. Now, the electron has 30 zeros before we get to a non-zero number. So if I wrote the entire mass of an electron out, again, 30 zeros before I get to a non-zero number, and this number is so big again, I even had to put the unit down below here. Now, if we write this mass of an electron in scientific notation, we would get 9.10939 times 10 to the negative 31st kilograms. So I want to make one final point, and that is this. This number that I just wrote out and the number with all of these zeros is the same number, okay? And the same thing can be applied to that first example in that the number with all of these zeros and the number that we wrote in scientific notation is expressing the same number. So just because we write it differently and we save some space with all those zeros does help factor into that same number. So both of them are equivalent. Now, we do have some rules that we utilize for writing numbers in scientific notation. So our first rule here is a general rule for scientific notation. And this general rule for scientific notation is when a number is bigger than 1. Our decimal in these numbers are going to move to the left starting at the decimal point. And the number of places moved to the left, or the number of places that decimal moves to the left, is the positive power of 10 when we express our number in scientific notation. Now, our other general rule here is when a number is smaller than 1. So when we have a number smaller than 1, the decimal moves to the right starting at the decimal point. And the number of places the decimal moves to the right is the negative power of 10 in scientific notation. Now, let's try these general rules about scientific notation in an example. So our first example says, express the diameter of the sun, which is 1,392,000 kilometers in diameter or length in scientific notation. So we get to the point here where we have to ask ourselves, is this number bigger or smaller than 1? Well, this is much, much bigger than 1, and so we can start with our rules for being bigger than 1. So it says if the number is bigger than 1, the decimal place moves to the left starting at the decimal point. Now, you can see here from this number, there is no decimal points. These are commas. Don't confuse commas with decimal points. So if no decimal point is shown on your number, we assume it's after the last number listed. So I'm going to emphasize this here with our decimal point, and I'm going to label it as our decimal point. And the rules then state that you start at the decimal and you move back to the left. Now, how we do this is we draw our little humps in each number slot. So what we're going to do, we're going to draw a line in between the decimal and that first 0, so 1 hump, then 2, then 3, then 4, then 5, and I'm going to stop here at 6. And the way I know to stop is because you stop when there is only one number that is to the left of the new decimal. Now, how we write this is we write all non-zero numbers involved in this particular number. So this number in scientific notation would be 1.392, and because these other numbers after this 2 are zeros, we don't need to include it in our scientific notation. So this would be 1.392 times 10 to a positive power, and the positive power is equal to the number of places the decimal moves, or these humps. So we have 1 hump, 2, 3, 4, 5, and 6. So this is going to be times 10 to the 6. And we always need to have a measurement, which means we need to have a unit. So our unit here would be kilometers. And that would become our answer. Now, what you can also do is double check yourself on the calculator. So if we have our number here, which is 1,392,000, and all I'm going to do is I'm going to press enter, which it's going to give us the same number. But if you have a Texas Instrument calculator here, a TI-30 calculator, what you can do is you can hit this second button. You can go over to where it says in this painted on writing, psi/ing, and then you scroll over using the arrow keys, you select psi, and you press enter. Well, now we get 1.392 times 10 to the 6, which is the same value that we have here. So we can always double check ourselves with our calculators. Now it says here, express the density of the sun's lower atmosphere in scientific notation. So we ask ourselves here, the density here that is given is much, much smaller than 1. So the rules for putting a number into scientific notation that is much smaller than 1 is you start at the decimal point, which it's given, and you move to the right. Now, the number of places moved to the right becomes that negative power. So all I'm going to do is I'm going to start at my decimal, and I'm going to go in between and make my humps. So I have 1 hump, 2, 3, 4, 5, 6, 7, and 8. Now again, how do I know how to stop? Well, when I have one number to the left of my new decimal, I stop. Okay? So that's how I knew how to stop there. Now, All we need to do is write down all the digits that are non-zero, starting with this 2. So we would have 2.8 times 10, and it would be a negative power because we moved from the left to the right, and that negative power is your number of humps. So we have 1 hump, 2, 3, 4, 5, 6, 7, 8. And it's a negative power because we moved to the right. And we always have to put our units. That was a measured quantity, so we have to keep it as a measured quantity by putting our units. Now again, if you're unsure about yourself and you have a scientific calculator, you can double check yourself. So what I'm going to do here is I'm going to put this number in my calculator exactly how it is written. So I have 0.10, 20, 30, 40, 50, 60, 70, and then I have 28. I'm going to press enter, which I'm in my standard mode, so it lists out all my zeros exactly how I have it written. And then again, you hit this second button, sci/ing. You scroll over to scientific, you press enter, and looky here. That number is 2.8 times 10 to the negative 8 power. Exactly what we found in our problem. Now we can go a little bit further with our scientific notation, and we can talk about adding and subtracting numbers in scientific notation. So, with scientific notation and adding and subtracting, what we need to do is this. To add numbers or subtract numbers in scientific notation, the exponents must be the same. Now, if those numbers that you're trying to add or subtract are not the same exponent, or the scientific notation does not express them in the same exponent, what you must do is rewrite the numbers so that all numbers have the same exponent. Now, to get all of the numbers having the same exponents, you need to use those general rules of scientific notation to accomplish this. Now, once all numbers have the same exponents, the coefficients, or remember where those numbers in front, can be added or subtracted. Okay, so let's put these rules of adding and subtracting in scientific notation to the test in a few example problems. Okay, so we get to our first example problems, and it says subtract the following: 7.35 times 10 to the second meters minus 2.43 times 10 to the second meters. The first thing that we ask ourselves is the power in the scientific notation of all numbers involved in the calculation the same. So the power, remember, is what we have listed in our superscript, or the small numbers above the 10. And we have a second power in our first number, and we also have a second power. That's good. So that means all we have to do is add these coefficients. Now, just as a reminder, the coefficients, or excuse me, subtract the coefficients. The coefficients are these numbers out in front of the times 10 to the power business. So I just want to make that note here that these numbers out in front are known as the coefficients. And so the rule just says, hey, perform, if they're in the same power, perform that mathematical operation. So all we need to do here is this. We need to take 7.35 minus 2.43. So I put 7.35 minus 2.43. I hit enter, and I get a value of 4.92. And then what I have to tack on to the end of this is the same exponent and power that we have used. So it's times 10 to the second, and we can't forget about unit. This was measured in m4 meters. Now, if you are unsure of yourself, if you are unsure of yourself, you can always do this calculation in your calculator. So what I'm going to do here is I'm going to have 7.35 times 10 to the second power minus 2.43 times 10 to the second power. I close my parentheses, and I get a value of 492. Now remember, that is not in scientific notation. So if I convert this over once again to scientific notation, I get 4.92 times 10 to the second, which matches up to what our answer is from when we just performed this calculation. Now let's go to a problem that involves a little bit more. It says, hey, add the populations of Tokyo, Mexico City, and Sao Paulo, Brazil. Now, these are listed here, and the first thing we have to ask ourselves is the exponents, or are the exponents of these particular towns' population the same? We have a 7th power, a 6th power, and an 8th power. Well, no, those are not the same, so we can't simply just add those coefficients together. We have to pick one number to convert all of these numbers to. Now, it doesn't matter what you do, but I see this very easily. 7 is in between our other two exponents. So what I'm going to do here is I'm going to leave Tokyo's population as is. So I'm going to leave it as 2.7 times 10 to the 7th. And then I'm going to take a look at Mexico City. Okay, so Mexico City needs to get to the 7th power. So it right now is 15.6 times 10 to the 6th power. We need to make this a bigger power. So how we do that? We move our exponent to the left. So what you're going to do here, the decimal is right here between 5 and 6. We're going to move it 1 over to get to the 7th power. Now by doing this, we get to 1.56 times 10 to the 7th. Again, if you move it to the right one, the exponent will go up 1. Now Sao Paulo, Brazil here, right now is at a population of 0.165 times 10 to the 8th. Again, we want to try to get the exponent to that 7th power. So what we do here is this. We start at the exponent. We want to go down 1, so that means we move our decimal over 1. This gives us a population of 1.65 times 10 to the 7th. Okay, so now what we are going to do, I'm going to underline these because we have a lot of numbers going on here. We have this. We are going to add together the coefficients of 2.7, 1.56, and 1.65. So in my calculator, what I'm going to do is I'm going to put 2.7 plus 1.56 plus 1.65. I press enter, and I get a value of 5.91. 5.91. They all use the 7th power, so we say times 10 to the 7th power. And remember, we are measuring the population, so that would be people. Now, once more, if you don't trust that you did this correctly, you can always utilize your calculator to go through these calculations. So what I'm going to do here is I'm going to add all of these exponents together in my calculator. So I'm going to have 2.70 times 10 to the power of 7, or the 7th power, plus our population of Mexico City, which is 15.6 times 10 to the power of 6, plus the population of Sao Paulo, Brazil, which is 0.165 times 10 to the power of 8. I press enter, and again, I get all these zeros, but I'm not in scientific notation. So what I need to do here is I need to get into scientific notation and check that out. just by adding these together and double checking our calculator, I get the same value of 5.91 times 10 to the 7th as I did through adding this together. So our rules do work when we add and subtract our numbers. All right, so let's go into our rules on multiplying and dividing in scientific notation. Okay, so we actually need to split our rules for multiplying and dividing in scientific notation. So we start out here with our steps to multiply in scientific notation. So the first step is a real simple step, and that's just multiplying the coefficients or the numbers out in front of your scientific notation. And once you've multiplied the coefficients, and written down that number, you simply just add the exponents. Now, like I said, we split multiplication and division for our scientific notation. So the next thing we'll talk about here is our steps to divide in scientific notation. So step number 1 is to divide the coefficients, or those numbers out in front. Then once you have divided the coefficients, you simply need to subtract the exponents of the divisor. Okay, so let's put these steps to the test in a few example problems. Okay, so our first problem here says multiply the following. We have 2 times 10 to the third times 3 times 10 to the second. So for our rules for our multiplication, it says multiply the coefficients or the numbers out in front. So what we're going to do is we're going to multiply 2 times 3. So 2 times 3 is 6. We write that down. We put that times 10 business. And then it says to simply add the exponents. So we have an exponent of 3 and an exponent of 2. So what we're going to do is add 3 plus 2. So 3 plus 2 is 5. And that would become our answer. Now we don't have a unit, but typically you would express this in a unit. Okay, so now we go down to let's double check ourselves, and then we will go down to that next problem. So again, what we have here is 2 times 10 to the third plus 3 times 10 to the second. We press enter. I'm not in scientific notation, so I change that to scientific notation here, and we get I added. Let me backtrack. Okay. There we go. So we get this value here. Again, we change that to scientific notation. We have 6 times 10 to the fifth. Very important here, just like me. Double check your numbers you punch into the calculator and the buttons you press as well. But this does verify that is the correct answer. So it says divide the following. We have 9 times 10 to the 8th divided by 3 times 10 to the negative 4th. So our rules for the division says divide the coefficients. So 9 divided by 3 is 3 times 10. And the rule says this. Subtract the exponent of the divisor from the exponent of the dividend. So that means we're going to take 8 minus a minus 4. So 8 minus negative 4 is 12. Okay, so again, that is our answer. We're going to verify it with our calculator here in just a second. So we take 9 times 10 to the 8th. 9 times 10 to the 8th. We subtract it from 3 times 10 to the negative 4th, and we press enter. Now, obviously here, and I did it once more. Make sure you have the correct symbol in that calculator. I did it twice here. And we get a value here of 3 times 10 to the 12th, with checks out here. Again, my mistake with the calculator in these two problems was I did not put the multiplication sign in this problem on top and the division sign on bottom. So when you verify via the calculator, make sure you put the right symbol in the calculator. Okay, so now we can go and we can kind of apply almost everything that we've done. It makes it really, with scientific notation, it makes it really easy to express really big or really small numbers, and it makes it really convenient for us to write down. Now what we can do here is we can go and we can have kind of this application of when might we go from one thing to another in our units. So that topic is dimensional analysis. And dimensional analysis is defined as a systematic approach to problem solving that uses conversion factors to move or convert from one unit to another. Now, we mentioned a very important thing in our definition here of dimensional analysis, and that is the concept or term of conversion factors. Now, a conversion factor is defined as a ratio of equivalent values used to express the same quantity in different units. Now, one key thing with our conversion factor is that a conversion factor must cancel one unit and introduce a new one. And what a conversion factor does is it changes the units of a quantity without changing their value. Now, conversion factors are used almost on an everyday basis, and the best way to see those are through some examples. So one is 1 dozen is equal 12 to a quantity. So if we had 1 dozen eggs, we would have 12 eggs. Or in cooking, 3 teaspoons is equivalent to 1 tablespoon. Now, percentages can also be used as conversion factors. These percentages relate the number of parts of one component to 100 total parts. Okay, so let's use our knowledge here about dimensional analysis and some things that we've already identified with SI base units to make some conversions. Okay, so in our problem here, we want to convert 48 kilometers to meters. So what you need to do here is we need to utilize this chart, which I provided in the periodic table packet we use this semester, and we are going to use these values, okay? So the first thing to do here is whatever value or number is given, we always start by writing that down. So I'm going to start out by writing 48 kilometers, and then we draw our conversion factor. So we put a time symbol, and then we just draw a line. Now somehow we need to relate kilometers to meters. So on this chart that I have provided, the periodic table packet for this semester, I'm going to look for our kilo, and I find it down here, and it says 1 kilounit equals 1,000 base units. So what that means for us is that 1 kilometer equals 1,000 meters. And remember, I should have noted this, meters is a base unit, okay? So I'll point that out in our next example. Now before we use these numbers, we need to cancel out units. Remember, that was a key thing mentioned in our previous page of notes. Conversions need to cancel out units and introduce a new one. So key thing here, diagonals always cancel out. So 4 kilometers, because it is in the top left corner, we need to cancel it out on bottom. So kilometers is going to be in that bottom spot. And then that new unit we're trying to introduce, meters, needs to go in that top spot. Now, all we need to do is plug these values into our conversion. So the number associated with kilometers is 1, and the number associated with meters is 1,000. And now we're ready to convert from kilometers to meters. So what we are going to do here, we're going to take 48 times 1,000 and then divide it by 1. So 48 times 1,000, and then we divide that by 1. And so we get a value of 48,000. Now, the unit in that top portion here will always become our unit. So that's 48,000 meters. And just so you know here, the diagonal units cancel out. So if you like to cross those out, those cancel out. Now we can convert 245 milliseconds to seconds. Now, again, I should have noted this on the first problem, but seconds and meters, those are base units. Okay? So again, I'm going to look on my value for milliseconds, and I'm going to relate it to a base unit of seconds. So I find milliunits. Okay, I scroll over. It says 1,000 milliunits equals 1 base units. Okay, so what that means for us is that 1,000 milliseconds equals 1 second. Now, we start out with this conversion by writing down what's given. So we start out with writing 245 milliseconds, and we draw the conversion factor, and then we cancel our units diagonal. So because we have milliseconds up here, diagonal from it, we need milliseconds. So we put milliseconds in our value there. Now we're trying to introduce a new unit of seconds. So seconds is what we need to place up top. And then we turn to what we just written down to go through this conversion factor. So again, there's 1,000 milliseconds in 1 second. So 1,000 is the number associated with milliseconds. We put 1,000 in this bottom portion because it is tagged with milliseconds. Now 1 is the number associated with seconds. So what I need to do here, this is saying 245 times 1, and then we divide that by 1,000. We have 245 times 1. I press enter. I divide that number by 1,000, and I get a value of 0.245. And our unit would be what is listed up top in seconds. Again, if you like to cancel out those other units, you can, and we would get our unit here. Now we got a little bit of a challenge, and I'll show you why. So we want to know the speed of an object that is currently traveling 550 meters per second, and we want to know that speed in kilometers per minute. Okay, so we're going to have to do a little bit more work to get from one point to another. The first thing that I want you to do, or the first thing I want us to do, is write down what we are given, and that is 550 meters per second. Now, I express this like this for a certain reason. That is because we are going to have to get rid of not 1 but 2 units, okay? So the first thing that I want to get rid of is this meters. So meters is up top. That means if we cancel diagonal, we cancel out meters, and we're trying to get to kilometers. Now again, we want to relate our base unit of meters to kilometers, okay? So again, you find kilo on your sheet here. So 1 kilo unit is equal to 1,000 base units. Remember, base unit here is meters, so that means 1,000 meters is equal to 1 kilometer. Okay? So 1,000 is associated with meters. We put 1,000 on bottom. And then kilometers is associated with 1. We put that on top. So what I'm going to do here initially is I'm going to take 550 meters per second times 1 divided by 1,000. So 550 times 1 divided by 1,000. Okay, so I get a value, if you didn't see that, 0.55. So 0.55. And now we need to talk about units. Our m's for meters cancel out. And so on top, we're left with kilometers. But don't forget about this unit of seconds. So we have per second. Now, this means because we want it in per minute, we're going to have to do another conversion factor. So what I'm going to do is I'm going to start out by writing this value of 0.55 kilometers per second down, and we're going to go through this next conversion. Okay, so we want not the time in seconds, but in minutes. So I'm going to draw my conversion factor, and we have to think a little bit different. So again, we need to cancel out seconds, and remember, diagonals cancel. So that means diagonals can go from bottom to top. So what we're going to do here is we're going to put seconds on top, and then what we want per minute, we want that on bottom. So now, the conversion is not in this particular chart, but we have to think about it, okay? We have a couple of things. We have minute and second. So we need to relate, okay, well, if we know 1 minute, can we identify how many seconds are in a minute? Well, it's 60. There's 60 seconds in a minute. So again, 1 is associated with minute, and 60 is associated with seconds. Okay, so now what I'm going to do here is I'm going to take 0.55 times 60, and I'm going to divide it by 1. And I get 33. Now we can talk about units. Again, diagonal units cancel out, so our units for seconds would cancel out, and we would be left with 33 kilometers per minute. So that's how we would do a two-step conversion. All right, so that is everything, all the information contained in section 2 of chapter 2. We learned a lot about the mathematical operations that we will use for measurements in this class. I hope you have enjoyed this video, and if you haven't done so already, make sure you subscribe.